Finite Element Machine was kind of a specialty that we worked at Langley, and it turned out that it was the right thing because commercial people then saw the promise of this, and the chips became less and less expensive, and once somebody demonstrated that you could do something, then they figured there's maybe a market out there. So one company that, well, I might say that at the time that we developed the Finite Element Machine, we did that, and then my year in Norway, the fellowship came, and so just before I left for Norway, we were putting in evaluations for different commercial machines to do the next generation past our Finite Element Machine. So it took like a year of procurement, so when I came back from the fellowship, it was just the final determination was made to go with this company called Flexible Computer because you could put in different type of chips. You didn't have to just use Intel chips. You could use National Semiconductor or whatever. So that's the idea of flexible. So we got one of the first flexible computers and developed our software on it. Now, the reason the Finite Element Machine was somewhat restricted was that we had to develop all the operating system ourselves. We had to develop all the compilers, all the libraries, and all the applications. So it was just a major development, all done here at Langley. But if you have a commercial one, that's even, you can cut back and do a lot more. So the flexible computer was commercial. The only problem was, how do you take advantage of all these parallel machines? Parallel processors there. It was very crude. There wasn't really software to do it. So we had a contract with Harry Jordan and at the University of Colorado, very innovative young fellow. And he came up with something called Force. I think if you watch the Star Wars stuff, there's Force and so on. So he came up with Force, and it stood for Fortran, which was commonly used for concurrent something. Force, F-O-R-C, concurrent execution. Yeah, that's what, Fortran for concurrent execution, which meant you can run many things in Fortran at the same time, which was really, really neat. So we first implement that on our flexible computer, and once we had that, then Cray came along and developed their first Cray 2 and Cray Y-MP. Well, we had our Force, which we could run our structural applications in. So I remember the day when somebody said, well, now we got this new computer at NASA Ames and the Cray Y-MP. Do you suppose you could solve, and we're working on the shuttle problem because the Challenger had the accident at that time and we're remodeling the whole solid rocket booster. So we were doing it on the flexible computer and using a VAX computer. Those are pretty primitive, and here comes this new computer at Ames. But could we take our Force first and put that over there, and then could we take our application? So I copied it over to our new computer, the Force, and then copied our application, and it actually all worked, just the first day. And so then it opened the world. We could solve huge problems and very fast, and something that formerly took many, many hours, probably 8 hours or something to solve on our machines at Langley. With this new Y-MP, when we got it all souped up, we could solve it in, we ended up solving it in 6 seconds, which meant that bumped through what then was kind of like a sound barrier, but it was called the gigaflop barrier, kind of where you do 1 billion operations in each second. So if a plane is flying across here, it goes about 100 feet and you're doing a solution. So anyway, in 8 seconds we were able to solve this 54,870 degree of freedom, it's called, or those X, Y, and Z problem, and that was so significant. It was the first engineering problem that had succeeded this gigaflop barrier. So Cray gave us an award for that, and out at the supercomputer conference. It was quite a thing back then to go through the gigaflop. Now you can get gigaflops on your desktop computers, but so now they're talking about teraflop barriers. So, and those have been broken, and it'll be petaflop. So that's kind of the history of where we were in structural analysis.